So Jai Hind, this is Ritesh Sharma from Ajay Kumar Garg Engineering College, Ghaziabad. I am teaching the subject Fundamental of Electrical Engineering in first year, and today I am going to discuss the topic the steady state analysis of AC circuits, part 1. So as we all know that in unit 2 we have the steady state analysis of the AC circuits. And to understand the concept of the combination of RL circuit, RLC circuit, it is very important to understand that how this AC circuit behave when these elements like resistance, inductance, and capacitance, when they are how they respond when they are connected to circuit alone. Okay, so that's why this lecture is very important to understand the concept of this. So let us discuss one by one. So this is my content is first the AC circuits containing the resistance only, the AC circuits containing inductance. This is the flow of our discussion. First we take the AC circuits containing the resistance only. Okay, so this is we know that the resistance is there and we are supplying or this voltage, this is AC voltage, that is VM, where Vmax is the maximum voltage, is the simple AC supply to this circuit. This is the equation. V is equal to Vm sin omega t, where V is we know that instantaneous value of V is the value of we call the instantaneous value, Vm is the maximum value, and omega t is the angle, or omega is the speed in radian per second. It's in form that. Now, when we supply the voltage in that, so there will be some current in that. So V, according to the Ohm's law, V is equal to I into R. V is equal to IR. Where I is the instantaneous current in that. So from this, we can say that I must be equal to V upon R, where V is nothing but the instantaneous voltage, that is Vm sin omega t upon this. So this is the current actually. Okay. So this Vm upon R, you can write it's a Vim, that is called the maximum value of current, because the maximum value of current will be there. Suppose this is the alternating voltage and this is the maximum value of the voltage, this at some angle theta is equal to 90 degree, and the current will be maximum, that is Vm upon R. R is the resistance of the circuit. So I is this I is equal to Im sin omega t, where Im is equal to Vm upon R. It's very simple concept. Okay. Now, from looking at both the voltage and the current equation, both voltage and current equation, we can say that the voltage and current are in same phase. They are in, because the phase of this voltage is 0 again, and the phase of the voltage is again 0. So they are in the same phase. So if we draw the phasor diagram of this, if we draw the phasor diagram of this, both the voltage and current, this is the current, this is the voltage, are in the same phase because they have the 0 at this instant. Now the waveform that you can see here, you can see that we have the 3 waveforms here. One is called the voltage. For voltage, this is the voltage waveform, that is Vm sin omega t, Im sin omega t, because the current and voltage in the same phase, so they will follow like this, although the current having some lower value. Okay, and this is the power for power. So let us first find out the power in the pure resistive circuits. So power in a pure resistive circuit is given by, or the instantaneous power is given by the power is given by P is instantaneous value of current and the voltage. P is equal to V into I, we know that. So V is equal to Vm sine omega t, and for current it is Im sine omega t. This is for the voltage and current. So we multiply the instantaneous value of voltage and current. So we got the Vm into Im sine square omega t, sine square omega t. So that is equal to Vm Im. You can write this 1 minus cos 2 omega t upon 2. We can take it over here, or again you can write Vm Im upon 2 minus Vm Im upon 2 cos omega t. So this is the average power actually, or it is called the instantaneous power. When you take the average of this is the constant term, constant. This is called the sum, which is the fluctuating power. So as you can see that this is the 2 omega. So as you can see here, this is the power. If you take the average of this, it's a cosine function so of having double frequency. So as I just told you that the power here in this term, if you take the average of this, will be 0. So only the power for the whole one cycle, that is average power, will be given by Vm Im upon 2 or Vm by root 2 multiplied by Im by root 2. That is called the RMS, Vrms into IRMS. And this will be the 0. Because for whole one cycle, for one period, that will be the 0 if you integrate it. So only this term will be remain. So this is the power in a circuit, that is voltage into current, where V and I are the RMS value of voltage and current respectively. So this is how we can calculate the power in a circuit. So this is the simple analysis of the circuit when only the resistance is there. And we know that as there is a voltage, the angle between the voltage and current is almost 0. So the power factor, which is nothing but the cosine of the angle between the voltage and current, will be cosine of 0 will be equal to unity. So for the pure resistive circuit, the power factor will be unity. This is very important. Okay. So after this pure resistive circuit, let us discuss the AC circuits containing the inductance only. Let us suppose we have one inductance only. This is the inductance we have. Now let us discuss the concept when there is a inductance only. So we know that when we apply the voltage, the current will be there, and the voltage, this is a coil, the inductance coil, which will induce some voltage, and that induced voltage, suppose this induced voltage will be minus L di by dt, and this induced voltage will oppose the applied voltage according to the Lenz's law. So this applied voltage will be equal to minus of this EL, and that's why it is L di by dt, which is V, where V is equal to Vm sine omega t equal to L di by dt. So from here, so di will be equal to the Vm upon L sine omega t dt. So when you calculate the current, when we are going to find the expression of this, of current, sorry. So current, when we integrate both, okay, over the period of time, you will get I will be equal to Vm is constant, IL is constant. So this sine omega t will be minus, when we integrate, it is minus cos omega t divided by omega L. This. Now you can write this. Minus cos omega t like Vm upon omega L into sine omega t minus pi by 2. So this current, you can see this is the expression of current, where this omega, or you can also write the Vm upon xl sine omega t minus pi by 2. So this xl is nothing but the inductive reactance. I can write it over here. So this xl is equal to omega L, which is called inductive reactance. So xl is equal to omega L. So this is the current expression, and now we can say that this current is lagging behind the voltage by pi by 2. So if you draw the phasor diagram of this, okay. So this is you can say that the current is lagging behind the voltage. This is the voltage waveform, Vm sin omega t. This is the dotted is the current waveform, which is lagging behind the pi by 2. So if you draw the phasor diagram of this, so that take the current, this is the current, voltage, which is taken as a reference, and the current is lagging behind the voltage by pi by 2. This is the 90 degree or pi by 2 current. So current is lagging behind the voltage by pi by 2. This. So here you can say that this is the two waveform of voltage and current lagging the voltage by pi by 2. Now, what about power? What about power? So power, power in pure inductive circuit, because whenever we have a inductance there, it is a pure inductive circuits. So for power, as I told you, we can calculate by taking the voltage into current. So V is equal to Vm sine omega t into Im sine omega t minus k pi by 2. So this means that Vm, Im, and then we have sine omega t, and this you can write is a minus of the cos omega t. So this must be equal to minus Vm into Im upon 2, that is 2 sine omega t into cos omega t, which you can write minus k Vm upon Im upon 2 sine 2 omega t. So when you calculate the average power throughout the cycle, you will find that this will be 0, because we have the sine omega t terms. So from this diagram, you can say that this is the cycle for the power. So one we have the positive cycle, one we have the negative cycle. So if you take the average of this, you will find that it is 0. Hence, the power in a purely inductive circuit will be 0. So average power will be equal to 0 in pure inductive circuit. And we know that as the angle between the voltage and current is 90 degree, and the power factor is cos phi, which is equal to 0. So again, in AC circuit, the power is given by, we know that is a VI cos phi. The cos phi is 0, the power is 0 again. So again, the power is 0. So this is the current AC through the pure inductance. Now coming to the capacitance. In capacitance, the waveform for the current, as you can see that this is the capacitor which is connected in the to this supply, and when we provide the current, this capacitor will first charge and then it will discharge. Okay. Now for the current, you can say that if you find the current expression, so we know that the charge is given by C into V. We know that Q is equal to CV. The charge is there. So C, that is Vm sine omega t. This is our Q, that is the charge, and we know that the current is given by dq by dt, the rate of flow of charge. So d by dt of this. So d by dt of this Q, which is your CVm sine omega t. So here you have to differentiate this to find the expression for the current, that is CVm, and when you differentiate sine omega t, you will get omega bahar, omega outside, and sine is cos omega t. And you can write down this Vm upon 1 upon omega c sine of omega t plus pi by 2. This is, you can write the expression for the current. Now you can see this part we can also again replace by Xc, which is called the capacitive reactance, sine omega t plus pi by 2. So where Xc is called the capacitive reactance. Xc is called capacitive reactance. Capacitive reactance Xc, which is equal to 1 upon omega c. Omega c. Now this is the expression for the current, which shows that the current leads the voltage by 90 degree plus pi by 2. So the way the phasor diagram for this will be, this is the voltage and the current which lead the voltage is by 90 degree. So this is by I. This is the 90 degree. So current lead the voltage by, since the phasor is going in anti-clockwise direction, so current lead the voltage by pi by 2. Again the power will be 0. Since the angle is 90 degree, the power will be 0. How? So when you calculate the power, this is the waveform for the voltage, current and the power. So for this, again when we calculate the power, we will find that the power is nothing but the Vi, or you can say that the V, that is Vm sine omega t, Im sine omega t plus k pi by 2, and you will find that is equal to Vm into Im upon 2. This is again the cos omega t, cos omega 2 omega t. Just a minute. So when you calculate this 2 sine omega t into cos omega t. Sorry. Seen that this current is leading the voltage by pi by 2. So let us, if we draw the phasor diagram of this, we will find that the current is leading the voltage by 90 degree. So the power in a circuit will be equal to V into I, that is Vm sine omega t into Im sine omega t plus pi by 2. So that is equal to Vm into Im by 2. So this is cos omega t. So 2 sine a cos a, we can write sine 2 omega t. So again we will calculate the average power for the whole cycle. We will find that we have a sine omega term, which is the fluctuating terms. So again the average power in a circuit will be 0. as you can also see from this particular diagram or the waveform, that for this period when the voltage is increasing, the current is decreasing till the voltage becomes 0. So when the voltage is become maximum, the current will be 0. Then when voltage decreasing, current will be going like this, and when the voltage 0, current will be peak in upward direction. So this is how for the one cycle, this will be the one cycle for this. But the power is going like this. So plus minus, so average power will be 0. Okay, so this is the you can say that the how can we find the power in a circuit. So power is there. So here the power factor, again you can say cos phi, that is the power factor. That is the power factor will be again 0, because it is the angle is 90 degree between the voltage and current. So cos 90 will be is equal to 0. So this is the. So now in this lecture we have seen that how the circuit will behave when the purely resistive, inductive and the capacitive elements are connected. Okay, so because this topic is very important to understand when we apply this concept to the combination of the circuit like RL circuit, RC circuit and RLC circuits. So thank you so much. I hope this lecture will help you. So Jai Hind.